We're going to talk about covalent bonds now, which, in contrast to ionic bonds, are a much more gradual encounter. So the ionic bond is an attraction of a positive cation with a negative anion, and in covalent bonds it's still about attraction of positives and negatives, but the electrons are shared in this case, so it's much more gradual. And this curve that I've drawn is a potential energy graph where it's energy going up on the y-axis and distance between nuclei, or the nucleus of each species, is increasing going to the right. So let's think about a hydrogen atom, which is simply a proton nucleus and an electron around that. And let's make our little cloud of the electron's position. And let's put another hydrogen atom, which has also a positive core and a single electron around it. Okay, so those are separate hydrogen atoms. And so the going out to the right on this axis is more separate nuclei, so they're separate. So as you go further to the left, the nuclei of the atoms get closer together, and the energy way out here is a constant because the two atoms are completely separate and there's no potential energy between them to speak of. But once they start getting closer, we find that there's an attraction, the potential energy decreases, like going down a hill. Okay, and at the bottom, the two nuclei are closer together, and the two electron clouds are overlapped, and this is just a schematic way of showing that, and you have the two electrons, which are then shared. And I'm going to have to get rid of this to draw it again. So we have the two positive nuclei, we have the two electrons, and we have a single overlapped cloud around them, and that is a hydrogen bond. So it's a hydrogen bonded to a hydrogen, and it's low in the potential energy. And this is a covalent bond, so they share electrons. Okay, and you can keep going closer and closer together, but as you get more close together, the nuclei get too close together and they start repelling each other. So the wall rises very quickly in energy. And at this position, you have two protons right next to each other, the two electrons around that, and then one cloud. And that's not a very stable condition because the two protons would repel each other. So the ideal distance is given by this portion, I can't do it, by the bottom of the curve. The distance between the nuclei is the ideal bond length between them. So that's bond length. And we can also talk about bond energy. Okay, the bond energy, which you might also call BE, and we talked about bond energy in terms of a Born-Haber cycle, and it's also known as bond strength and bond enthalpy. So, and this refers to the energy required to break a bond. And it's always going to be positive because a bond is a stable thing. Okay, you have the bottom of this curve is the stable energy of the bond, and since this energy up here is the separated nuclei, then the bond energy is actually the distance from the bottom up to the separated atoms. So that is the bond energy. That distance in energy is the bond energy. And it's always positive because it always takes energy to break a bond. So I probably shouldn't put the bottom arrow in there. It really should just be up. It's an energy going from the bond up to separated atoms. Okay, now let's look at some more specifics. And let's look at bond length. Okay, so the bond length is actually just the separation distance of the nuclei. So however far apart they stay. And so let's take a carbon atom. Okay, and this is my carbon atom. And it has a nucleus in it. And here's another carbon atom. And let's compare it bonded to fluorine and bonded to bromine. Since fluorine is a much smaller atom than bromine, the distance between the nuclei from the carbon to the fluorine is going to be smaller. Okay? And this distance than the distance between the carbon and the bromine, just because bromine is bigger. So we say that the bond length for CF is less than the bond length for CBr. And so that's comparing fluorine to chlorine, so two things in a group. We can also compare relative magnitudes of bonds to the same two atoms. We have single bonds sharing two electrons. We have double bonds, and we have triple bonds. Okay, this is sharing 2 electrons, this is sharing 4 electrons, and this is sharing 6 electrons. And so this is for the same two atoms. And we can look at how the potential energy curve changes for those in this curve down here. So a single carbon-oxygen bond has some length and depth, and so the length, remember this is the distance between nuclei, and it turns out that the single bond is the greatest length because it shares the fewest number of electrons. Double bond is in the middle, and triple bond is the shortest because it shares so many. So if we say bond length is the distance to this point, to the bottom of the curve, okay, then we can go a little further down. And we can see that if this is where the two repel each other, then the distance, the first distance, that's not what I wanted. The first distance is the C triple bond O. And the second distance is C double bond O. Oops, that's a triple. Should be a double. And then finally the last one is going to be the single. And that goes that distance, so it's longer. Okay, so we can also label the curves up here. This one is a single bond, this one is the double bond, and this curve is the triple bond, and you can see that the bottom of the wells changes, and actually the depth of the well changes. The single bond is not as deep, it's not as strong of a bond as the double bond, and that's not as strong of a bond as the triple bond. But they all have the same place out here because they're all separate carbon and oxygen atoms out here. It doesn't matter what kind of bond they are. They're the same energy out here. But when they get to be bonding, it depends how many electrons are shared. Okay, now let's compare ionic to covalent bonding in another way, which is in terms of melting points and boiling points. Okay, so we're going to look at what we know about ionic compounds, which is that they appear in lattices. So here's sodium chloride in a lattice, and when you melt or boil this, you end up with separate sodium chloride species in space. You break the lattice in order to melt it. That's how it becomes liquid or, with enough heat, gas. Okay, so you're breaking ionic bonds. if you melt or boil, which gives them very high melting points. Very high melting points and boiling points. Okay, that's in contrast to molecular species, which are covalently bonded. Okay, so if you look at water, liquid water, which is a covalent compound, and you see that you have H2O, you have a unit of H2O, and within that unit you have covalent bonding. But between that unit and another H2O, I've drawn dotted lines between them to represent, and I'll draw circles around the separate waters. The dotted line represents the forces between them, which are not covalent bonds. They are weak intermolecular forces. So only weak intermolecular forces are broken when you melt or boil. And those, since they're weak, it doesn't take nearly as much heat. Okay, not covalent bonds. What you're breaking are these dotted lines, which are intermolecular forces, to form separate water molecules. Therefore, even though covalent bonds are strong, you're not breaking those when you boil. So molecular compounds which are covalently bonded will have relatively low melting points and boiling points, which is why ionic compounds tend to be solids at room temperature, whereas covalent compounds tend to be liquids or even gases at room temperature, because it doesn't take nearly as much heat to make them boil or melt. All right, so time for you to try something. Based on atomic size, which you already should know the trend for, rank the following bonds in order of bond energy and bond length. So I'll let you try that. All right, so let's look at these. They all have a nitrogen. Okay, so all we're looking at is what the nitrogen is bonded to. This is an oxygen, a fluorine, and a nitrogen. And we know that going across the periodic table, it goes in the order NOF across the periodic table, and we know that they get smaller. Atoms get smaller going across. Therefore, fluorine is the smallest, followed by oxygen, followed by nitrogen. So we know that length is based on size, and so the fluorine can get closest, so it's going to be the shortest, followed by the oxygen one, followed by the nitrogen one. Bond energy is basically the opposite trend, because the shorter the bonds, the harder they are to break. So we can just simply reverse this. The nitrogen-nitrogen bond is the weakest, and the nitrogen-fluorine bond is the strongest. And we can actually compare those on a chart. There's charts of average bond enthalpy. Whoops, went too far. So we'll go back to that. And this is something you will be using from your textbook or from elsewhere. So we can look at the enthalpies are listed in energies of kilojoules per mole. And so we can right here compare nitrogen-nitrogen, nitrogen-fluorine, and nitrogen-oxygen, and see that the energies, anyway, are smallest for nitrogen-nitrogen, then oxygen, then fluorine, just like we predicted.